Okay, by the end of this video, you should be able to explain the term arene and aromatic, describe and explain the models used to describe benzene, and review the evidence for a delocalized model of benzene. Oops, wait, there should be an E on in there. Okay, so arene, first of all, is a hydrocarbon compound containing benzene rings. Okay, and a benzene ring is this thing here with 6 carbons, and we draw a circle through the middle, and that is C6H6. Okay, so each carbon is bonded to one hydrogen that's not been shown. Okay, and if a compound is aromatic, that means anything containing a benzene ring. Okay, so slight difference there. So an arene is a hydrocarbon compound containing a benzene ring, and aromatic is anything containing a benzene ring. Obviously, aromatic is to smell, so that's originally why these compounds were named. These compounds containing benzene rings are quite smelly, but not any longer, or not only scientifically. Okay, so we'll name some examples. Okay, and let's have one with 2 groups. Obviously this there is just a CH3 off the side. Okay, and this is bromobenzene, then chlorobenzene, and we've got nitrobenzene. And then here, what we do when we're naming compounds based on benzene with more than one group off the ring, you number the carbons. So we're going to say this carbon is 1, 2, 3, 4, 5, and 6. And then we say that this is 3 bromo methyl benzene. Okay, so we don't say that 1 methyl benzene, because if you say like something like chlorobenzene, nitrobenzene, methyl benzene, you assume that that group there is on carbon 1, and then bromo is on the 3rd one from it. Okay. Some uses for benzene. It is used in polystyrene. So the polymer chain for polystyrene contains benzene, and it's found in phenols as well. Okay, so phenols are compounds have a lot of use. Okay, so we're going to have a look at the evidence people use to discover benzene and to work out its structure. So evidence here, or evidence for structure. Okay, so in 1825, somebody worked out that its empirical formula, so by doing percentage by mass of this compound, was CH. Okay, CH, 1834. The molecular formula was worked out. And it was found to be C6H6. So it has a molar mass of 78. So MR 78. And this basically suggested it contained alkenes. So empirical formula CH, molecular formula C6H6. So suggested presence of alkenes, but people had already discovered alkenes by now, and the difference with benzene is that benzene would not react like alkenes. So classic reaction of alkenes is decolorizing bromine water, and benzene didn't do this. Okay? And in 1865, Kekulé proposed that this was what benzene looked like. He said it looks like this. It's got 3 double bonds and it's in a ring. Okay, but his model did not explain the reactivity. So he said, "Oh, it's cyclic and it's got 3 double bonds," but he couldn't say why it didn't react with bromine. Okay. And so he went away and thought about it for a while, and later on he then proposed something slightly different. And he said, actually, what happens is you have this, and it changes to that. So the double bonds move. So the double bonds move between those two, and they go back and forth, and that's why it's stable. And he said the resonance. So think of your frequencies and your resonance. So resonance between the two gave it stability. Okay, so that was his explanation. Okay. Okay, and so this was an idea, and most people accept this. They thought that was pretty sensible. But then, in 1922, following new techniques being invented and things like that, X-ray crystallography, so before DNA was discovered, evidence found all of benzene's bond angles and bond lengths were the same. Okay, so all the bonds were the same length and all the bond angles were the same length. And according to Kekulé, these would be different. So if you had double bonds and single bonds, they would be different lengths. Okay, so so double bonds are shorter than single bonds in reality, and a carbon next to with a double bond is going to have different bond angle to this carbon here. Okay, so this was a bit strange, and there was one other piece of evidence that was quite odd as well, and this is in the hydrogenation. Okay, and this is the key piece of evidence that gave benzene its modern structure. Okay, so they had this thing where they said, well, all the bond lengths are the same, all the bond angles are the same, so it can't quite be these two flipping back and forth, and they used the evidence from hydrogenation to work out exactly what happened. So if you take cyclohexene and you add hydrogen and you make cyclohexane, delta H of this reaction is minus 120 kilojoules per mole. So we're going from cyclohexene to cyclohexane. But if you take this compound here, and that is cyclohexa 135 triene, and you add 3H2. Therefore, to make cyclohexane, delta H should be minus 360 kilojoules per mole. because you've got 3 double bonds. And Kekule was saying that we've got cyclohexyl-1,3,5 triene, but that it switches back and forth between the 2 different forms of it. Okay? However, for benzene, delta H is equal to minus 208 kilojoules per mole. So really different reaction. And what that means, if we think of an enthalpy profile diagram, so we take enthalpy H, and the Kekule structure, the cyclohexyl-1,3,5 triene, is up here. Benzene is further down here, and cyclohexane is here. Okay? And these models suggest that it takes minus 360 to get to there, and minus 208, that difference there. So there's a difference here of 152 kilojoules per mole. So what we can say is benzene is 152 kilojoules per mole more stable than Kekule structure. Okay, so they know it's cyclic, they know all the bonds are equal and all the bond angles are the same, and that it's C6H6, but for some reason it isn't quite what they think it is. Okay, so it's more stable, so that's why it's less reactive, and this led to the final correct model of benzene. Okay, and that's where they came up with this compound. Okay, we're going to talk about what this means next lesson. Okay, but you need to be able to, describe all those different bits of evidence and explain what they meant in the history of benzene. Okay.